So it's really my really true honor to introduce the next speaker, Rick Schoen, to whom I am very fortunate to have as my PhD advisor. And he will talk about how minimal surfaces and MOTS singularity affect relativity theorems.
Thank you, Lon. So let me first thank the organizers for the conference, and also I'd like to wish Yvonne a very happy and healthy birthday, and I'd like to add my thanks to her for pioneering this field that we all work in. I think we owe her a debt of gratitude. So so thanks, Yvonne, and happy birthday. Okay, so today I'm going to give just a kind of informal talk on some of the ways in which singularities that occur in volume minimizing hypersurfaces and MOTS affect theorems in relativity. And actually, for the different cases, they occur in somewhat different ways. And in some cases, they can be gotten around without too much trouble. And in other cases, they present much more difficulty. And so I'm going to talk about 4 theorems. So the first one is the Riemannian positive mass theorem. And the second one is the reduction of the space-time positive energy theorem, which I'll just abbreviate to to 1, the Riemannian positive mass theorem. And the third one is the Penrose inequality, the Riemannian Penrose inequality. And the fourth one is the space-time positive mass theorem. The argument using MOTS. Okay, and so so the space-time positive mass theorem was a theorem of EHLS. That's Eichmer, Huang, my introducer, and Dan Lee and myself. The first 2 of these were developed by with Yao. The arguments were developed a long time ago, and the Riemannian Penrose inequality, of course, has 2 separate proofs. In the 3-dimensional case, there's the inverse mean curvature flow by Schoen and Ilmanen. And then there's the Bray approach, the Bray flow. And the Bray flow was extended to higher dimensions by Hugh Bray and Dan Lee. They did it in greater than or equal to 3 and less than or equal to 7. So, and this theorem also, EHLS, works for the same range, 3 less than or equal to n, less than or equal to 7. Okay, and so the sort of elephant in the room in the mean curvature approach to these theorems is the fact that they're dimensionally limited by the possibility that the hypersurfaces you construct can be singular. And so on the one hand, we know some things about the singular sets and their structure, but in certain cases they cause rather difficult problems. And so in the case of 1, so the proof of 1, actually one of the main ingredients of the proof was described in briefly in Sven's talk the other day, and this one uses minimal slicings. And so the idea, or what one has to do from this point of view, at least what works is that if you take a manifold, so this is the Riemannian positive mass theorem. So it's really a theorem about manifolds with positive scalar curvature, non-negative scalar curvature, and it involves looking at families of hypersurfaces. So one chooses sigma n minus 1, and this is chosen to be a volume minimizing hypersurface, oriented. Volume minimizing, and then there's the lowest eigenfunction of the Jacobi operator, the linearized operator, is used to define a weight function, and then there's a hypersurface in there constructed. So this one is a weighted volume minimizer. And I won't go through the details of this because I'm not going to talk about this. I'm not going to talk about the details of this. In fact, I actually gave a series of talks on this here at ESI in, I think, 2017 on trying to do this in the case of singularities. So what happens? So the difficulty is that in this problem, when n is greater than or equal to 8, it's possible that this sigma may have a singular set. So there may be a set of singular points S contained in sigma n minus 1. Now the set S is relatively small. It's a closed set, and its Hausdorff dimension is less than or equal to n minus 8. But nonetheless, it's there. And so in this argument, when you construct the next slice, you have to worry about the possibility that the next slice may hit the singularities of the previous one. And so this creates major problems. And actually, the proof of the positive mass theorem involves slicing down to 2 dimensions ultimately. So you have to do this process. And so I described in 2017 some work with Yao, where we developed the slicing theory in the presence of singularities, and we showed that you could do the slicing, and when you got down to the lowest dimension, you actually got a smooth surface. And so in that way, we were able to get around this problem, but it's pretty hard work. It's a difficult theorem. The singularities really cause problems because you have to consider these the slicing, which these lower dimensional submanifolds. Okay, and so that's the situation. That's how the singularities affect the case 1. Now, in case 2, which actually I'm going to talk about in some detail, is really the main technical thing I'm going to talk about today. In this case, when people ask me, I remember somebody asked me in 2017, how about the equation? So this reduction uses the Zhang equation. So the Zhang equation is a graphical equation, and it never has singularities. So in any dimension. So my answer was always a glib. Well, it shouldn't be a problem. It should work out, right? So I'd like to actually explain that it really does work out today. And so I'll come to that later. I don't really have much to say about 3 and 4, but let me just say that, so I wanted to say one other thing, which this issue also came up in Sven's talk. So although these singularities occur, there are results in low dimensions that tell you that they're somehow non-generic. So if you take a mg and you take a sigma contained in there, say it's compact, or it could be non-compact too. And so sigma, say, minimizes in some class. It minimizes either with boundary or in a homology class. So those are the relevant conditions. Then it can happen for a metric G that sigma could be singular, but you can ask the question, suppose I'm allowed to perturb G a little bit. So can I perturb G so when I perturb G to say G tilde, then when I do the minimization for G tilde, of course, I get a slightly different surface, right, because I'm minimizing for a different metric. And so you can ask, can I perturb the G tilde so that the corresponding minimizer, sigma tilde, is actually regular, is smooth. And so believe it or not, we don't know the answer to that in general, but there's an old theorem, actually it's based on work of Hart and Simon, who did this in the case of the plateau case. So if you have just surfaces, hypersurfaces bounding with boundaries in Euclidean space. So they showed you could perturb the boundary to make the minimizer smooth in dimension 8. So the lowest dimension in which you can have singularities is dimension 8. And so the Hart-Simon argument was generalized to Riemannian manifolds by Nat Smale. So this goes back to the 80s. And so Smale showed that in fact you can perturb the metric so the singularities go away. And so that's of course a very useful thing. In particular, in case 1, in the Riemannian positive mass theorem, it eliminates the necessity of considering the slicing entirely. I mean, if you could take the slices to be smooth, then everything just works beautifully, as it does in low dimensions. I haven't really told you how it works, but then the only problem really in high dimensions is the singularities. Okay, and very recently, this was also done in dimensions 9 and 10. So this is a very recent work by Otis Chodash, Montelides, and Felix Schulze. So that means also in case 1, you can get around the singularity problem just by perturbing metric slightly. So the assumptions involved in 1 are inequality. So you're allowed to perturb the metric a little bit. And this was done just this year, I think, 2023. On the other hand, their argument appears to have no chance of working in higher dimensions. So the case of dimension bigger than 10 is still a complete mystery. It doesn't resolve the issue in all dimensions. And let me also say that this sort of generic regularity doesn't necessarily help in the other cases. It's not clear. I mean, it would have to be formulated. It would have to be formulated somewhat differently. For example, I think it would be a lot harder to show that MOTS are regular generically, because MOTS are not minimizers of a variational problem. And so the way this sort of thing is done is you perturb the metric to sort of force the hypersurface to move in some direction. You make the metric smaller in certain directions, and you do that. With MOTS, it's not so clear that you could do something like that, but it would be, of course, interesting to do. Okay, so that's all I'm going to say about case 1. Now, case 3, which is the Riemannian Penrose inequality. Just a few words, the issues there. So one of the issues is that there's a construction of a flow. It's called the Bray flow. And so this has to do with an asymptotically flat spacetime with a non-negative scalar curvature, but with a horizon, with a stable or outer minimizing minimal surface. So this sort of picture. And this horizon, and the Penrose inequality says that the mass is bounded below by a constant times the square root of the area of the horizon. So the Bray flow involves deforming this picture by a conformal change of metric in such a way that you deform the metric and then you minimize, again, produce a new horizon, and by taking the steps small enough, you produce a continuous flow with some jumps, with some singularities. But the key ingredients of the Bray flow, so first of all, there's the question, so I think the first issue is constructing a weak solution of the flow. Now, I have a feeling you can do that, because even though the constructions in low dimensions use the fact that the minimizers are smooth and you have estimates on them, and they work in sort of smooth topologies. But on the other hand, minimizers in higher dimensions, although they're not everywhere smooth, there still are natural norms in which you can get continuity. You just don't expect to get CK convergence across the singular set. Yeah.
When you say weak solution, what type of variational principle would be associated?
Yeah, so it would have to be a family of metrics which in a weak set satisfies that the flow. So the flow has the property, the Bray flow has the property that the horizon area remains the same, and the other key steps is a weak solution. So there's the monotone property of the mass under the flow. So the key thing is that the mass decreases. And so the proof that the mass decreases, it presents another problem. So if the horizons are smooth, that argument is sort of tricky because it involves actually, Lorenzo presented the Bunting-Massoud argument. So the proof that the mass decreases is very similar. It's a reflection argument across the horizon, and it becomes compact on the other side. And then the positive Bray observed the positive mass theorem for that reflected solution actually implies that the mass decreases under the flow. Okay, so the key thing, I mean, the decrease of the mass is the key thing, and then eventually the flow converges to Schwarzschild. So that's how the Bray-Lee method works. And so it would involve proving a positive mass theorem in this sort of reflected case where you get this horizon, which now may have some singularities, and then you did the reflection across. And so that looks like a rather tricky issue to me to prove that. So this may have some singularities. And again, as far as I can tell, for this Bray flow, the generic regularity doesn't really help because you have a family of surfaces, and so unless they're all regular, it's not clear that it's really useful. Okay, and then finally, the case 4, which is the spacetime positive mass theorem. So that one involved. So we sort of mimic the Riemannian, the original proof of the Riemannian positive mass theorem by constructing a minimizing hypersurface between two planes, assuming the inequality does not hold. So we showed that if the mass is bigger than the linear momentum, then you could in fact construct between two planes a minimizing or stable MOTS, strongly stable MOTS. So this surface in here. Stable MOTS. Now, in low dimensions, when everything is smooth, the way you could then proceed is to use the stability to conformally deform that MOTS to non-negative scalar curvature with smaller energy. Okay, and that's how the argument goes. So then ultimately it reduces. So you have to construct the conformal deformation, which involves solving a linear PDE, and then you have to do the case 1. It reduces even to case 1, and so it seems to me that the only way to do that would be to slightly generalize the stuff in case 1. So I think case 4, this fourth one is harder than 1. So it would also involve a singular slicing. I mean, you would have singularities in the MOTS, and then you would have to do the conformal deformation again for the singular metric, and then you would have to do the slicing. So this is somewhat similar to 1, but I haven't really worked out the details of that, so I don't really have anything to report on it. But I think it's doable if with enough work. Okay, and so what I want to talk about is the one I claimed should be okay, right? which is 2, and so let me describe that. So 2 involves the space-time positive energy theorem. So you look at an initial data set, mgk, and it satisfies the dominant energy condition. So that means mu is bigger than or equal to the norm of J, where I think people have written these down before. So mu is the observed mass density. It's 1/2 the scalar curvature minus the square of the second fundamental form plus the trace squared, and J is the divergence minus its gradient of the trace. So I won't write them down again. So this is the inequality that in the Riemannian case reduces to non-negative scalar curvature, but in general, it's a more complicated condition involving both G and K. Okay, and so the way we did that reduction is to consider this equation, which we call the Zhang equation, because we found it in a paper of Zhang, who was a student of Garrosh, who was trying to prove the positive mass theorem. And so he proposed this equation, and then he didn't really succeed in doing anything with it. But we realized that this equation is very relevant. So the idea of the Zhang equation is you consider a higher dimensional space. You consider M cross R. We call the variable here T in R. And then you extend the data. So we take on this the product metric, d plus dt squared. And then we just extend K in a trivially. So we extend K so that it's independent of the of T. Okay, so in that way we get a higher dimensional. We could think of it as an initial data set. Of course, it's not asymptotically flat or anything. But then what we do, so of course M sits in here as M cross 0, and so the idea is to try to find to look at graphs over M. Okay, so we look at the original M now, which is T equals 0 in this product, and then we can imagine deforming M by looking at graphs, right? So we can take a function f M, and then we can look at the graph of f G. So that's a new hypersurface, and it's a new n-dimensional manifold with its metric. So we would then have the induced metric on the graph. So the graph is t equals f of x. X is a point below, and so we have the metric on the graph. And assuming the function is asymptotic to 0 or asymptotic to a constant, the graph would be asymptotically flat, the graph metric. And so the idea is to solve an equation for f which sort of cancels out the second fundamental form k. So what we want to do is get rid of the k. And so the way that Zhang proposed to do that is to study what is essentially the MOTS equation on the graph. So we could look. So remember, if we have a surface in a space like a surface in a space like hypersurface, a hypersurface in M, then the MOTS equation says that the mean curvature of that surface is equal to the trace of the ambient second fundamental form restricted to the surface. Okay, and so we impose that condition. So the Zhang equation is the equation. So we can write it in a couple of different ways. It's the condition that the mean curvature of the graph is equal to the trace. So I've continued to call it K, but remember K is now defined on M cross R. It's the trace of the restricted to the graph of the extended K. That equation, or if we write it out explicitly, so H of f, the mean curvature, we can write in two forms, either the divergence form, div grad f over square root 1 plus norm grad f squared, or we can also expand it out and write it as g upper ij minus fi fj over 1 plus grad f squared times the Hessian Dij of f divided by square root. Okay, and this trace G of k is just the trace with respect to the induced metric. So this expression here is, let me call it G bar upper Ij. So G bar is the induced metric. G bar lower Ij is Gij plus Fi Fj, the derivatives, right? So the inverse matrix turns out to be that. Similarly, on the right-hand side, this would be G bar upper Ij now times Kij, where Kij is now restricted to the graph. And so that's the Young equation. And what we showed is that the stability condition on the graph as a MOTS. So as a graph, the MOTS is automatically stable. It has a strong stability condition. And we showed that the stability condition on the graph implies implies this inequality. And so let me write down a formula. So that the integral over the graph of mu minus j, and then plus 1/2 times minus the scalar curvature of the graph, and then plus norm, let me call it h squared. This thing. This phi squared is less than or equal to the integral of gradient phi squared. G bar, right, on the graph. And so this is the inequality. Now, the dominant energy condition says this is non-negative. In fact, in some cases, we'll want to make it positive. And this is the scalar curvature of the graph. This is a positive term. The sign's right? Yeah. So this is a good positive term, which we could throw away, but actually we're going to use it in a minute. So this is the condition, and again, as in the talk on Monday, I think the stability on the graph and with the decay, if we had a solution, is such that you can put functions phi in here not only of compact support, but you can also allow phi to be asymptotic to 1. So for phi of compact support, or phi minus a constant, phi minus 1, say, of compact support. So in other words, you can allow a vertical translation. And so that's important for doing the conformal deformation. Okay, and so in the smooth case, assuming the solution exists, you can use this to conformally deform. So then the idea, assuming everything is smooth and we have existence, there exists a U, which is a solution of the conformal Laplacian. So the conformal Laplacian is the operator LU, so let me call it LU for conformal. And so that's the Laplacian on the graph of U, and then minus a constant C of n times the scalar curvature of the graph, and then times U. So we want to solve that equation with U asymptotic to 1. At infinity. Now this constant C of n is the magnitude's important. So the constant C of n, it turns out, is always less than a quarter. So this is n minus 2 over 4 times n minus 1. And so notice it's smaller. In fact, even less than a quarter. It's smaller than the half that appears here. And so it's not difficult to show that this inequality implies that the conformal Laplacian has lowest eigenvalue positive. So it's an invertible operator in particular. appropriate spaces, and that enables you to solve this with a positive u. So this u is positive. And moreover, the vertical translations allow you to show, so in general, this u, we assume good asymptotic, so u at infinity is the form 1 and then plus a constant, a over x to the n minus 2, and then plus lower order terms. X goes to infinity, and the possibility of using vertical translations enables you to show that this a is actually negative. Okay, so you can control the sign of a because of the possibility of these translations. It's a simple argument. I won't go through it, but it enables you to do that. So in general, okay, and so in general, this a, when we solve the graph is asymptotically flat, and it actually has zero mass because the original, we assume the original decay is like a Schwarzschild decay. Then when we do the hypersurface, that decay is smaller than the decay that would give us any mass. So the mass of the graph is zero. So when we look at the conformally deformed metric, u to the 4 over n minus 2 times g bar, then this one has mass which comes entirely from a, and so it's a constant times a. I guess it's 4 over n minus 2 times a. Right? So that's the mass of g bar, and this mass is negative. And moreover, this metric has zero scalar curvature. Or we could say it another way. Yeah, let's say that. Zero. So what we've constructed an n minus 1 dimensional initial data set, zero scalar curvature, so it's a Riemannian, satisfies the Riemannian dominant energy condition, and it has negative mass. And so that reduces, that reduction reduces the proof of the positivity of energy for the space-time case to the Riemannian case. So that's the idea. And so in particular, the solutions of this equation, this graphical equation, never have singularities. So the graphs have bounded slope and so if you can construct them, and they'll be singular. So the types of singularities that occur for minimizing hypersurfaces are never graphical. Okay? Not except of course in higher codimension they can be, but in codimension 1 they're not graphical. So in particular, it appears that singularities don't matter, but actually they do matter a little bit because it turns out the existence theory is the solution doesn't always exist. So there's so the existence theory is a bit more complicated than you might hope, and that is that what happens is that what happens when you try to solve the equation is that you can't get soup estimates. There's no bound on the height that you can get. And so what we did is we regularized the equation. We realized if you look at the regularized equation, if you took a positive number, call it S, where you take h of f minus trace k equals s times f, then when s is positive, you can actually get height estimates just by simple maximum principal arguments. So in this, when s is positive, you always get a height estimate, and you can in fact use that to solve the problem. So there exists this solution fs, where fs tends to 0 at infinity. It can go up pretty high, but always finite. It could go down pretty low. But near infinity, it's very well behaved. So fs would, again, tend to 0 at infinity, and it would decay like a harmonic function. So the decay is like 1 over x to the mod x to the n minus 2. So we can do fs. So then of course you have to look at the limit as s goes to 0. And what we proved is that the limit exists so it exists outside a compact set, but the solutions can blow up. So in general, the existence picture is like this. So if this is M, then there's some domains which needn't be connected. Omega plus, some domain omega minus. These are compact regions. The boundary of each region is a stable MOTS. Well, both of these are stable MOTS. The difference between the plus and the minus is in one case it's a future MOTS, and in the other case it's a past MOTS. And the solution actually blows up. So the solution exists outside outside here. So F, the limit of Fs, it exists there, and it's nice near infinity. But what happens on the positive part is that F is infinity here. And on the negative, the boundary of the negative regions, F is minus infinity. Okay, and so the way it looks, and you can analyze it pretty in some detail, at least in the smooth case, and that is that on the positive regions, it can blow up asymptotically to the cylinder. And on the negative regions, it can blow up asymptotically to the cylinder, blowing up to minus infinity. And so this surface on which it blows up and which it approaches is just a MOTS cross R. The surface is S plus cross R, and this one, the cylinder would be S minus cross R. So you see, whenever you have a MOTS in the original solution, in the original data set, you can take its product with R, and you will get a MOTS in the product space. Okay? And then that MOTS could, it's not graphical, but it's almost graphical. It's vertical. So you could imagine that it could be a limit of graphs. And in fact, that's exactly what happens in the problem. And so that's the existence there. In fact, you can give examples where the solution doesn't exist. So it's not just that we haven't done it well enough. It occurs, the blow up. So in fact, actually, the blow up was later used by several people, Anderson, Metzger, and Mikhail, to actually construct MOTS. So the only real way we have of constructing MOTS is as asymptotic solutions of the Young equation. So you can, in some cases, force the solution to blow up, and you can use that to prove existence for MOTS. So MOTS, again, it's not variational. And so you can't get them by minimizing anything. And so that's the picture. And so unfortunately, singularities do happen here, right? So it could happen that these that there are singular sets here on these MOTS. So there could be a singular set. So there could be some singular points on the MOTS. Now, I should say the only MOTS we know how to construct are ones that, well, they're stable, but they also are what's called lambda minimizing. Okay, and this just follows from the Young equation. And what it means is that there's a constant lambda, so that if I take my MOTS, say S, and I compare it to some other, I'd look at a comparison surface, say S1, then the volume of S is less than or equal to the volume of S1, so they agree outside a compact set, and then plus lambda times the volume between the two. So between the two, there's some region, say R, the region R. So that's sort of the picture. I mean, in general, they can cross, and so the R is really an n-dimensional current. It can have plus and minus signs. But now this condition of being lambda minimizing is really almost as good as being minimizing. So from a regularity point of view, the singular structure of these is the same as for minimizers. So the reason is because the volume of the hypersurface scales like r to the n minus 1, but the volume inside, enclosed, scales like r to the n. So when r is small, the volume between is negligible. So if you blow these up, so if you look at a possible singular point here, then you can prove that you can blow up and you get a tangent cone, and that tangent cone is actually volume minimizing. And so in particular, ultimately the regularity theory in codimension 1 reduces to the question of whether there are non-trivial tangent cones. And so you can do that also for lambda minimizers. So in particular, the regularity properties would be the same. So again, the dimension of the singular set is at most, again, n minus 8. So these occur in dimension 8 and higher. And so on the other hand, the graph itself is smooth. So what's happening is that the singularities here, which of course I'm producting with r, so this whole line is singular. So these are limits of the graph. And so what's happening is when I go way down here, the graph is smooth, but it's getting very rough. So it's getting, the second fundamental form is blowing up as I go down near these singular points. And so even though it's smooth, it's not sort of uniformly, second fundamental form isn't uniformly bounded near there. And so how do we handle these? Well, so actually, Yao and I in our original paper just did the case n equals 3. We did it, so this was done way back 1981, I think. And so what you can observe is that if the MOTS is stable, this MOTS is stable, then it means that the conformal Laplacian, so remember the operator we're interested in is Laplacian minus C of n times r, and we can look at that on the graph, and we could look at it on the cylinder over the horizon. And so this operator has, minus it has positive first eigenvalue. Well, okay, so there's an issue about it being 0. So it's convenient at this point to have the strict dominant energy condition, which we claimed in our paper and was later justified. We didn't have it quite right, but it was justified in the mainly through Lon's work in the EH and maybe Mikhail. Okay, so anyway, this we can make strictly positive. So otherwise, there's a borderline case here that you have to kind of worry about. And so in particular, this implies, so let's call this number minus lambda. So this implies that if you look at at solutions on the graph just in separated variables, we're interested in positive solutions. So there are sort of two obvious positive solutions. So the Laplacian on the graph, of course, is just d second dt squared, and then plus the Laplacian on the MOTS, on S. And so when you do separation of variables, you see that there are two solutions, that one blows up exponentially and the other decays exponentially at infinity, and these would be this phi 1 of x, where phi 1, which is now positive, is the lowest eigenvalue. So L phi 1 is minus lambda 1. Lambda is positive, and so you get two solutions like that on the MOTS, and so then the idea. Okay, so then what you want to do is show that you can find solutions that behave like that on the graph. So for example, let's just focus on one of these. Get this one. This on one of these. So you then want to show that on the graph you can find solutions. So what we want to do really is to find two solutions. Call it U0 and U1. They're both solutions of L U0 is 0. This is now on the graph. And you want U0 to be the decaying solution at infinity. So U0 tends to 0 as t goes to infinity. You would expect it to be asymptotic to e to the minus square root lambda lambda t as t goes to infinity, and I want it to go to 1 at the spatial infinity. As x tends to infinity. And it's a solution of the conformal Laplacian, whereas u1 will be the exponentially growing solution. So u1 will go to infinity as t goes to infinity, and it will go to 0 as x goes to infinity. Okay, and so if I just use u0 to conformally deform the metric, what I would be doing is conformally compactifying this. So if I used u0, I would conformally compactify, and then I would get this singular point. I would get a space with a singular point, which you have to fiddle with. And so we discussed that in the three-dimensional case, and then Mikhail extended the arguments to. So these were done for n equals 3, we did it, and for 4 less than or equal to n less than or equal to 7, it was done by Eichner. And so the key observation is that for this u0, you can again do what we did for the in the smooth case. So u0 tends to 1 at infinity. The stability implies that. Again, that u0 at x is 1 plus a over mod x to the n minus 2, and then plus lower order terms. And again, it implies that a is negative. So u0 has that property. On the other hand, u1 at spatial infinity goes to 0. So u1 of x is just some b over mod x to the 2 minus n minus 2. And then plus lower order terms. Okay, and so what you can do is you can avoid the problem, that singular problem, just by making a complete metric. So you can, let's see. So you could look at, if I looked at u0, if I look at u, which is u0 plus epsilon u1, and I choose epsilon small enough, then the term involving the fundamental solution would then be a plus epsilon b. A is negative, so if epsilon's small, this still has negative contribution. So this would be, this contributes. So u would again be 1 plus a plus epsilon b over mod x to the n minus 2, and then plus lower order terms. And this number is still negative if I choose epsilon small enough. And so in particular, what we can do, and now this function of course is bounded below. In fact, it grows exponentially as you go to infinity. So in particular, the space-time, if I consider m minus the omegas, omega plus omega minus, and I consider the metric u to the 4 over n minus 2 times g bar, the graphical metric, then I get a space with some number of n's. So corresponding to each MOTS, I get an extra n. And well, the n's are not those n's are not asymptotically flat, but that doesn't really matter. They're actually pretty well behaved n's, and so there's one asymptotically flat end. So I get this sort of picture. There's a nice asymptotically flat end, and then the other ends, are big, asymptotically flat. So this end sort of flares out. It's not not asymptotically flat necessarily, but the point is that this is a complete manifold. It has some extra ends. That doesn't really matter. So this has negative mass, and it has scalar curvature 0. Okay, and so again, that contradicts the Riemannian positive mass theorem. So when you do the Riemannian positive mass theorem, when you construct the minimal hypersurface, you have to worry that it might run off on some other end. But because the end is quite big, it's easy to show that doesn't happen. In fact, these ends actually have convex boundaries if you go out far enough. so you can do the usual proof and get the contradiction. So that's how the reduction That's how the reduction went. So that's in the case that the MOTS is smooth. So I'm assuming these are smooth in order to construct the eigenfunction and these solutions that blow up and decay. So now what I want to claim is that in this particular problem, you can actually do the same thing on a singular MOTS. And so to motivate that, let me prove a sort of baby theorem where the singularities don't matter. Okay, and so this is a theorem which is not really interesting geometrically because they're much easier proofs, but I just want to illustrate it to show that there are certain properties that singular hypersurfaces have that are quite similar to smooth ones. Oh, I should have said one thing. There's another step in the proof here. Actually, I'm almost out of time. 3:30. Oh yeah. Okay. Sorry. Yeah, I went too slowly. Okay. There was another step in the proof which really doesn't work at all in the singular case, and that is that I think in both of these both papers we actually deformed the graph so that it was identical with the MOTS near infinity, and that made it easy to construct those functions. So to handle the general case, you'd have to do that, but you can do that construction without that step. Okay, and so what I want to claim, and I won't have time to get the proof. That's the price of Blackboard talks. Let me write what I claim. The claim is even if the MOTS is singular, you can make that construction. You can find corresponding U0 and U1. So of course they don't have pointwise decay estimates, but they decay appropriately. So U0 again has the same property that at spatial infinity it has a negative potential term, and U1 has the property that it goes. Actually, U1 will go to infinity as t goes to infinity. So we can construct those functions, then we can make the same argument. Okay, so that's the sense in which the singularities for this problem don't matter. And let me explain. Just close the talk with kind of a baby example. So you can prove. So if you take a minimizing hypersurface in Mn, and if Mn has positive Ricci curvature, say Ricci positive, let's say it's a compact hypersurface, sigma n minus 1, then stability implies that the integral of Ricci nu, the unit normal, so this would be on the regular part, and then plus the square of the second fundamental form. Phi squared. And so in particular, if Ricci were positive, we could get a contradiction just by choosing phi equals 1. And then we would show that there can't be a stable hypersurface for positive Ricci. And well, it doesn't have, I mean, the conclusion one could draw using the existence theory is that the n minus first Betti number, or the n minus first integral homology is 0, but that's equivalent really to the first Betti number being 0, which is an old theorem from the 1940s of Bachner using harmonic forms. And so it's just a very complicated proof of a theorem that's been known for many years. But actually, in this case, when n is large, the argument works for all n. And so why is that? Well, the reason is because the singular sets is codimension 8. It's codimension 7 in the hypersurface. And minimal surfaces have nice volume properties. So they have the property that if you take a small ball, minimizing surfaces, then the volume of the surface inside there is bounded by a constant times r to the n minus 1. It's like the Euclidean volume for small balls. And so you can use a sort of Besekovich covering argument and cover the singular set by a finite number of disjoint collections of balls, and you can do that. You can use that to construct a cutoff function. There exists a function zeta, which is 0 near S, and say zeta is identically 1 away from S. And you can do that in such a way that the integral over sigma of the norm of gradient zeta raised to the pth power is less than epsilon. You can do it for any p, in fact, less than 7. In particular, you can do it for p equals 2. And so, in particular, although you can't directly put in the function 1, you can approximate it by, by functions so that the Dirichlet integral tends to 0. And so then using that, using a choice of zeta like that, you can make this side arbitrarily small, and this is positive, so you get similar contradiction. Now, the idea of the argument here is similar. So you can actually use this to show that these operators, so if we consider, say, the conformal Laplacian, which is the one we care about, so actually, this argument, if you look at it carefully, you also have to use, there's some other things. There's a Sobolev inequality, which holds on a minimal hypersurface. But using that stuff, you can actually show that on a singular hypersurface, the Laplacian has a discrete spectrum. So you can diagonalize the quadratic form, the Dirichlet form on L2. Everything works just as for a smooth manifold. And it's also true for the conformal Laplacian. So it has a discrete spectrum. So in particular, even in the singular case, you can construct this phi1, this eigenfunction, which is positive. Well, you don't know its pointwise behavior near the singularities, but it's positive and it satisfies the same equation, and then you can analogously construct the exponentially growing and decaying solutions. Then there are several other properties which are important. So you can also show, and this is a rather uses some somewhat subtle properties, but you can show that, so phi1, of course, is in L2, it's an eigenfunction, but you can actually show that it's bounded below. So in other words, it doesn't go to 0. There are no sequences of points going to 0 near the singularity. So in fact, phi1 has a lower bound. Actually, this is done in the slicing paper that I mentioned earlier. In fact, you can even show that phi1 tends to infinity near the singularities. So at singular points, phi1 not only is bounded below, it will actually go to infinity. Okay, and so anyway, I don't have time to explain, but I claim using that property you get on the cone, on the cylinder, you get these exponentially decaying, but only in the L2 sense. The L2 norm would decay exponentially and exponentially growing, and then you can make the same argument. So in other words, I claim you can remove the dimensional restriction for this reduction of the space-time theorem to the Riemannian theorem. Okay, well, I was going to give a little more detail on that, but maybe it's just as well. So let me stop there. Thank you.